Have you ever thought about how we actually 3D print solid metal parts, for things like jet engines or custom medical implants? This is a whole different world from your standard desktop plastic printer. We're talking about a process that uses a super high-powered laser to literally melt fine metal dust, building an object up layer by microscopic layer. The technology that makes this all happen is called Direct Metal Deposition, or DMD. And the real secret, the key to getting it perfect, well, it all comes down to one critical component: the nozzle.
So here's how we're going to break it all down. First, we'll get into the core challenge of printing with what is essentially metal dust. Then we'll meet the two main nozzle designs, the off-axial and the coaxial, and see how they really stack up. And finally, we'll dive into the hard data to see how engineers pick the absolute right tool for the job.
Okay, let's just get right to the heart of it. The basic problem in direct metal deposition sounds like it's straight out of science fiction. Seriously, how do you take a cloud of superfine metal powder and a beam of pure light and actually turn them into a solid, functional metal part?
At its core, DMD is this incredible fusion of technologies. You've got the precision of computer-aided design, the raw power of lasers, and the science of powder metallurgy, all working together. A laser creates this tiny little molten pool on a metal surface, and then a stream of powder is shot right into that pool. As the laser moves, it leaves behind a solid track of metal. You do that thousands of times, and boom, you get a complex, fully dense part with almost zero wasted material. And that right there, that is the million-dollar question. The entire process, the quality, the strength, the efficiency, the cost, it all hinges on this one single action: delivering that powder. If you get it wrong, you're just wasting incredibly expensive material, and you end up with a part that's full of flaws. But if you get it right, you can build the impossible. And the device that has to pull this off flawlessly every time, that's the nozzle.
So when it comes to designing these nozzles, engineers basically came up with two main solutions. And you can really think of them as two totally different philosophies for solving the exact same problem.
Okay, so on one side, you have the off-axial nozzle. It takes a direct side-on approach. Super simple, but it has one critical weakness. It's unidirectional. Then on the other side, you've got the coaxial nozzle. This one surrounds the laser with a cone of powder. It's a much more complex design, but it offers a total game-changing advantage. It's omnidirectional, meaning it works exactly the same no matter which direction you move. Let's dig into that.
All right, first step, let's talk about the off-axial nozzle. This is the simpler, more direct of the two designs. The easiest way to picture this is to just think of a garden hose. You're aiming it from the side to hit a very specific spot on the ground. With the nozzle, it's the same idea. It, or sometimes a few of them, are positioned at an angle to the laser, feeding a stream of powder into that melt pool. It's really straightforward and mechanically pretty simple. But, as you can probably guess, the direction you're moving the laser head suddenly becomes a very big deal. So right away you see this classic engineering trade-off. Because it's simple and cheap, the off-axial nozzle is perfect for basic jobs, like applying a coating to a part that's just rotating in a circle. The direction never changes. But the huge drawback is that its performance completely depends on that direction. The second you change course, the quality and even the shape of what you're depositing changes. This also means it's not very efficient. You can end up wasting 30, even 50% of that really expensive metal powder. So to get around the big limitations of the off-axial design, especially when you're trying to build really complex 3D parts, engineers came up with the coaxial nozzle. It's a way more sophisticated approach. Okay, so instead of that single hose from the side, now I want you to picture a circular sprinkler head. The laser beam shoots right through the center, while the nozzle creates this perfectly formed cone of powder that converges on that tiny melt pool from all sides all at once. It's a brilliant design because it guarantees that the powder delivery is completely uniform no matter which way the laser head is moving. The payoff for this more complex design is huge. You get true omnidirectional capability, which is absolutely essential for building complex 3D components. The quality is consistent no matter what the toolpath looks like. This design also boosts powder efficiency way up, often over 80%. So, what's the catch? Well, it costs more and it's more complicated. But for high-stakes industries like aerospace, that kind of precision is just non-negotiable. Okay, so we have these two design philosophies, but how do these differences actually play out in the real world? Let's look at the numbers. Now, what's really fascinating here is that even inside the coaxial family, the small design details matter a lot. Here, we're comparing a continuous nozzle, which creates a smooth, seamless cone of powder, against a discrete one, which uses a few separate jets. And you can see differences everywhere, but one number just leaps off the page: particle velocity.
Wow, just look at that difference. It's not even close. The continuous nozzle fires powder particles at over 11 meters per second. That's more than 3 times faster than the discrete nozzle. So why does that matter so much? Well, think about the surface of that tiny molten pool. It has surface tension, kind of like a bead of water. If the powder particles hit it too slowly, they can literally bounce right off, and that's just wasted material. That higher velocity gives them the momentum they need to punch through the surface and actually join the melt pool.
And this quote from the research just nails the physics of what's happening. That higher velocity from the continuous nozzle directly leads to higher efficiency. It empowers the particles to overcome the melt pool's surface tension. It's this incredible intersection of fluid dynamics and material science happening on a microscopic scale. So here's the bottom line. There is no single best nozzle. An off-axial design might be the smartest, most cost-effective choice for a simple coating job, but for a complex aerospace part made from an expensive superalloy like Inconel, a continuous coaxial nozzle that gives you maximum precision and minimal waste is the clear winner. The choice is a critical engineering decision that affects quality, time, and, of course, money.
And all of this leads to a final, really powerful idea. As we keep pushing the limits of what we can make, progress isn't just about bigger and more powerful lasers, it's about the microscopic choreography of the material itself. And the humble nozzle, it's right at the center of this revolution. So the real question isn't just what we can build today, but what new materials, what impossible shapes will be unlocked by the next perfect stream of powder.